Hi all, this video is going to take you through the Aqueous exam for 2019. So starting with question 1, you're given an equation for chlorine reacting with water produces HCl and HOCl. You're told hypochlorous acid is a weak acid. Explain the difference between strong and weak using these as examples. Include equations in your answers. So hopefully you all know the difference. Strong acids fully dissociate in water, which means they fully break apart. Every single acid that you put into water will break apart. So with HCl as an example, we use a full arrow to represent this. Every single HCl that we stick in water will break apart into a chloride ion and a hydronium ion. Weak acids, on the other hand, they only partially dissociate. So what that means is when you stick a whole lot of weak acids into water, only some of them will break apart. So using HCl as an example, when you stick that in water, equilibrium arrows, they show that it only partially dissociates. Some of them will break apart into the hypochlorite ion and the hydronium ion, but the majority of them will just stay as HOCl. So number 2, rank the species present for HCl and HOCl. So for HCl, if you start with that one, because it's a strong acid, when the HCl goes into water, none of the HCl is left behind. All of it turns into the chloride ion and the hydronium ion. So the concentration of the chloride ion is equal to the concentration of the hydronium ion. And because you're dissolving it in water, water naturally contains a small amount of hydroxide ion. So there's a very tiny amount of hydroxide ion in there. Alternatively, if you want to put the concentration of hydronium ion as slightly larger than chloride, because there's naturally some hydronium ion sitting in water, you can do that. And again, that's much larger than the concentration of hydroxide. But both of them are correct. With HOCl, because it's a weak acid, most of it stays as HOCl, so that's the largest concentration. Because it breaks apart into one OCl and one H0+, those two concentrations are equal, so HCl minus is equal to H0 plus. And again, because water naturally contains a little bit of hydroxide, there's a tiny bit of hydroxide floating around. Part 3, justify your rankings with reference to your answer in A2. Basically, it's just writing down what I said before. So HCl fully dissociates, that's why there's no HCl left. Cl minus and H0 plus are formed in equal amounts, because for every one HCl you form one Cl minus and one H0 plus, and then there's naturally some hydroxide floating in water, and then it's the same for HOCl. So just listen to what I said in the words as I was explaining part 2. So on to part B. Calcium fluoride is a sparingly soluble salt. Write an equation for the dissolving of calcium fluoride in water. So when calcium fluoride dissolves in water, we always use equilibrium arrow to show this. You form calcium 2 plus ions and 2 fluoride ions. And part 2, write the solubility product expression for calcium fluoride. Solubility product is Ks, and in this particular case it's concentration of calcium 2 plus ions multiplied by the concentration of fluoride ions squared. And the reason why it's squared is because we have 2 fluoride ions up here. Alright, on to part 3. Show by calculation that the solubility product of calcium fluoride is 4.13 times 10 to the 11. So your Ks expression, this is what we're going to use to try and calculate this, is the concentration of calcium ions multiplied by the concentration of fluoride ions squared. So the first thing we need to do is try and work out what the concentration of the calcium ions and the fluoride ions are. And the way we work this out is we use some of the information that we're given in B. In part B we were told that there was 0.00170 grams dissolved in 100 mils. So to work out the number of moles of calcium fluoride, number of moles is mass over molar mass, which in this particular case is 0.0017 divided by 78.1. Chuck that in your calculator, you get 2.17 times 10 to the minus 5 moles. Once you have the number of moles, you can work out the concentration. Concentration equals number of moles over volume. So 2.17 times 10 to the minus 5. The volume you were told was 100 mils, so 100 mils in litres is 0.1. Chuck that in your calculator, you get this number here, moles per litre minus 1. So going back to our Ks expression, concentration of calcium fluoride is 2.17 times 10 to the minus 4, this thing here. So when calcium fluoride dissociates, we know it produces 1 calcium ion, therefore the concentration of the calcium ion is that. And if you look back to your original equation, for every 1 calcium sulfate, you produce 2 lots of fluoride ions. For calcium fluoride, you produce 2 lots of fluoride ions. So the concentration of fluoride ions is 2 times 2.17 times 10 to the minus 4. Okay. And we still have to square it because the definition of your Ks expression is to have it squared. So chuck that in your calculator, you'll end up with 4.13 times 10 to the minus 11. Now, some of you may have taken a shortcut. Some of you may have noticed that calcium fluoride is an AB2 type salt, 1 positive ion for 2 negative ions. And when you have that particular case, you can use the little formula they give you, Ks equals 4S cubed. So 4 times the solubility, which is the same as the concentration that we worked out just before, cubed. And when you do that, you get the same answer of 4.13 times 10 to the minus 11. Alright, part C. A solution contains equal concentrations of fluoride ions and hydroxide ions. A dilute solution of calcium chloride is slowly added to this mixture. So you've basically got a beaker that contains fluoride ions and hydroxide ions, and you're adding in calcium ions. And you're trying to work out which of the salts is going to precipitate first. Are you going to form calcium hydroxide or are you going to form calcium fluoride? So what you need to know is we're looking at the Ks values. So what Ks values measure, or it's a measure of solubility. So the Ks value of calcium fluoride is smaller than the Ks of calcium hydroxide. Okay, because times 10 to the minus 11 is smaller than times 10 to the minus 6. What this means is that calcium fluoride is less soluble, and if it's less soluble, it means you need lower concentration of calcium ions, therefore the calcium fluoride is going to precipitate first. Okay, so Ks is smaller, means it's less soluble, you don't need as many ions for a precipitate to form, therefore that one is going to precipitate out. Alright, question 2. Lead pipes can result in a relatively high concentration of lead ions in water. 200 ml sample has a concentration. Calculate whether precipitate of lead chloride will form when an equal volume of 1 mole sodium chloride is added to the water. So when you guys did this experiment, most of you did the correct process where you work out Q, and then you try and compare the value of Q to Ks. But where you stuffed up is because you're mixing 2 liquids together, the concentration of the liquids is going to change. Okay, so the volume of the liquids is going to get higher, and as the volume changes, the concentration is going to change. So your very first step is to work out the new concentrations. So the new concentration, if we start with lead ions, and you can use a little shortcut, it's the original concentration times the old volume over the new volume. So in this particular case, the original concentration of lead ions was 2.7 times 10 to minus 8. The original volume of lead ions was 200 mils. The new volume, once you mix the 2 liquids together, is 200 plus 200, which is 400 mils. And chuck that in your calculator and you get a concentration of 1.35 times 10 to the minus 8 moles per litre minus 1. Now, some of you may be asking, do I have to put this in litres? And the answer is no. Because it's a ratio, as long as they're both in the same unit, it doesn't actually matter. Right. New concentration of, what are we doing, chloride ions, is the original concentration, which you're told is 1, times the old volume. So you're told that there's 200 mils of sodium chloride. Your final volume is 400 mils. So 1 times a half is 0.5 mole per litre minus 1. Okay, your next step is to write your Ks expression or your Q expression. So lead chloride, when it dissolves in water, you form lead ions and 2 lots of chloride ions. So your Q expression is going to be lead ions multiplied by chloride ions squared. So concentration of lead ions is what you worked out up the top. Concentration of chloride ions is what you worked out up the top. And we square it, and that gives you a value of 3.375 times 10 to the minus 9. So your next step is to compare Q to Ks. So the Ks value you're told is 1.7 times 10 to the minus 5. So we can see pretty quickly that Q is less than Ks, and if Q is less than Ks, that means you do not form a precipitate. If Q is greater than Ks, it means you do form a precipitate, and if Q is equal to Ks, then it means you've got a saturated solution where nothing else is going to dissolve. Alright, part B, lead hydroxide, sparingly soluble salt. Explain what would happen to the amount of solid on addition of a small volume of sodium hydroxide or a large addition of sodium hydroxide. So, again, with these solubility questions, the first thing you need to write is an equation to show what happens when it dissolves in water. So lead hydroxide will break apart into lead ions and hydroxide ions. That's your very first step. That normally gives you an achieved. Don't think it did in this case, but normally does. So when we add a small volume of sodium hydroxide, you are adding hydroxide to the system. And if we look at this equilibrium expression, we can see that it contains hydroxide. So when you add hydroxide, the system doesn't like it. It's going to try and minimize the change. It's going to try and use up all of that excess hydroxide. So, oops. So the system doesn't like funny stylus that you added OH minus, so it tries to use it up. And the only way it can use up the hydroxide is to favour the reverse reaction. And as you do the reverse reaction, as you go from this side across, you produce more lead hydroxide. Because you're producing lead hydroxide, you would form more lead hydroxide. Alright, number 2, addition of a large volume of 1 mole per litre sodium hydroxide solution. So when we use a large volume of sodium hydroxide solution, or you're talking about a high pH, you're getting into complex ion territory. Okay, so lead ions, if you have enough hydroxide, you can form a complex ion which looks like this. It's 1 lead ion, 4 hydroxide ions, lead's 2 plus, hydroxide is 1 minus. Because there's 4 of them, that gives you an overall charge of minus 2. Okay, so the lead ions can react with hydroxide to form the complex ion. And what this does is it removes hydroxide from the original equation, i.e. from this equation way up here. The system doesn't like that you're removing it, so the system tries to replace the lost hydroxide, and the only way it can do that is by favouring the forward reaction. Therefore, more lead hydroxide dissolves. Right. A laboratory technician needs to make a buffer solution with pH 9.1. Give the pH range over which the resulting solution will function as a buffer. Okay, so range of a buffer is pKa plus or minus 1. So 9.1 plus or minus 1 equals 8.10 to 10.10. Part 2. Calculate the mass of ammonium chloride that needs to be added to 1 litre of ammonium solution to make a buffer with pH 9.1. Okay, so all classes should have gone through an example of this. It comes up every second year normally in an exam, so please practice these types of things. There's two ways of doing it. I'll go through the proper method first and then I'll do a little shortcut later. A buffer solution, it contains acid and conjugate base. So in this particular case, the NH4 plus is acid and the conjugate base is NH3. But what you do is you treat it like a weak acid calculation. So ammonium ion, when it reacts with water, forms NH3 and H3O plus. And if you write your Ka expression, over NH4 plus, you get this. Okay, and then you go through and work out what you know. The Ka, we're not told the Ka, but we're told the pKa up here. So you guys need to know how to convert pKa to Ka. So it is 10 to the minus of whatever the pK is, so 9.25. Okay, concentration of the ammonia, you're told is 0.250. Now, the reason why we don't have to change the concentration in this particular question is because we are adding, where are we? We are adding a solid to a liquid. And you're told that assume there's no change in volume. So because the volume of the ammonia solution is not changing, it is staying as 1 litre, the concentration of the ammonia doesn't change no matter how much ammonium chloride you add to it. So the difference between this question and part A of question 2 is this is adding a solid to a liquid, whereas in part A you were adding a liquid to a liquid, and that's why the volume changed. Right, so going back to here, we know the concentration of ammonia, the concentration of hydronium, you're told the pH is 9.1, and we know to go from pH to H3O plus is 10 to the minus of that. And NH4 plus, that is what we're trying to work out. Concentration of the ammonium ions is going to be the same as the concentration of ammonium chloride. So make sure you can use your calculators, make sure you can do algebra. You get a concentration of the ammonium ion as 0.353 mole per litre minus 1. Okay, and then we can just work our way backwards. Work out the number of moles of ammonium ion, concentration times volume. Concentration, the volume is 1 litre, so it's nice and straightforward, 0.353 moles. And then number of moles equals mass over molar mass. So the number of moles is 353, mass is your unknown, molar mass you're told is 53.5, and work that out in your calculator, you get 18.9 grams. Alright, shortcut method. So the shortcut method is using a formula, and the formula is pH equals pKa plus log base over acid. Now you have to remember this formula, which is why I don't use it, because I always get the formula mixed up. I can never remember whether it's base over acid or acid over base. But if you're willing to put in the time and remember this formula, it's pretty straightforward. pH you're told is 9.1, pKa you're told is 9.25, concentration of the base is 0.25, and concentration of the acid is what we're trying to work out. Move that over to there and you get minus 0.15 equals log 0.25 over acid, and to get rid of a log you go 10 to the power of. So 10 to the power of 0.15 equals 0.25 over acid. Therefore the concentration of the acid, which is your NH4 plus, equals 0.353. And from there, you just stick that number into your formula up here. Alright, part 3. Explain whether the buffer in 2 is better at buffering the addition of small amounts of acid or small amounts of base. So, what I need to stress here is you don't compare the pHs to 7 and say that because the pH is 9.1 there's too much base, and that's what a lot of you actually did. So at pH equals pKa, which in this particular case is 9.25, that is where the concentration of the acid is equal to the concentration of the conjugate base. Okay, so when the pH is equal to the pKa, that's when you have equal amounts of acid and base. Okay, because 9.1 is less than pKa, that means we have too much acid. And therefore, it's going to be better at buffering. Oops. Better at buffering base. Okay, if the pH was 9.25, it would do acid and base equally well. If the pH was greater than 9.25, then it would buffer acid better than base. Right, question 3. 25 mils of 0.15 mol per litre methanoic acid is titrated against potassium hydroxide. So, you've got a little container of methanoic acid, and then you've got your burette, which is full of potassium hydroxide. So, part 1, calculate the pH of methanoic acid before any KOH is added. So, we're just trying to calculate the pH of this liquid in here. So, you need to recognise methanoic acid is a weak acid. So, weak acids, when they dissolve in water, you get that. And if you write your Ka expression, you get this. Okay, so whenever you've got a weak acid or a weak base calculation, always start off by writing an equation to show what happens when it dissolves in water, and then you write your Ka or your Kb expression. So now we start plugging in our numbers and what we do and what we know and what we don't know. So Ka, you're told the value, which is nice and easy, 1.82 times 10 minus 4. And the concentration of your methanoic acid, you're told, is 0.15. Now, up the top, if you look at this equation, for every one of these, we produce one of these and one of those. So these two things, the concentration of these two are the same. In reality, that's not quite right because there's a little bit of hydronium just floating around in water, but the amount of hydronium floating around is so small that we can just ignore it. So we therefore change that to H3O plus squared. And using your high-powered mathematics, you get 2.73 times 10 to the minus 5, and if you square that, root that, you get 5.22 times 10 to the minus 3, and your final step is pH equals minus log H3O plus, so minus log of that equals 2.28. That's a funny 8. That's a horrible 8. There you go. Alright, part 2. Determine the pH of a solution after 12.5 mils of KOH has been added. So hopefully what you notice is that both of the solutions are 0.150 mol per litre. Okay, and what that means is if we add 12.5 mils of potassium hydroxide, we're halfway to the equivalence point. And the second thing you might notice is that methanoic acid is a weak acid, potassium hydroxide is a strong base. So when you do weak acid and strong base, you form a buffer solution. And with buffer solutions, the pH at your halfway point is equal to the pKa. In this question, we're not told the pKa, we're told the Ka, but pKa is equal to the minus log Ka, which ends up 3.74. Now, quite a few of you actually got 3.74 as your answer for A, but unfortunately it didn't give you any credit. Alright, number 3, calculate the pH of a solution at the equivalence point. So the equivalence point is when all of the original acid has been dissolved. Okay, so if we look at our equation, methanoic acid plus potassium hydroxide goes to sodium methanoate plus water. So the definition of the equivalence point is when all of the acid has reacted. So in your little flask you have no acid. In your little flask you have no base because it's all been used to neutralize the acid. You've got lots of the sodium methanoate and you've got lots of water. So at the equivalence point, the only thing that is contributing to the pH of the solution is the sodium methanoate. Because there's no methanoic acid, there's no potassium hydroxide, they won't affect the pH. Water is neutral, so this is the only thing that affects the pH. So we need to know how much of that we have. And looking at our equation, for every one of these, we produce one of those. So the number of moles of methanoic acid is equal to the number of moles of sodium methanoate. So to work out number of moles of methanoic acid, it's concentration times volume. Concentration, you're told in the question, is 0.15. The volume you're told is 25 mils. So convert that into litres, divide by 1,000, and that gives you this many moles. And because we know the number of moles of methanoic acid is equal to the number of moles of sodium methanoate, the number of moles of this is also 3.75 times 10 to the minus 3. Alright, working out the concentration of the sodium methanoate, number of moles over volume. And in the question, we started off with 25 mils. Because the two concentrations are the same, we need to add 25 mils of potassium hydroxide. So we have a total volume of 50 mils in the flask. So 0.05, and that gives you 0.075 mole per litre minus 1. So your next step, you need to recognise that sodium methanoate is a weak base. So the first thing we do is write an equation to show what the weak base does in water. Now the sodium ion is a spectator, which is why I haven't included it. It's just the methanoate ion that actually does anything. OH minus. Okay, and once you've written your equation, you can write your KB expression, which is products over reactants. So one product, two products, and your reactant is HCOO minus. Okay, and from here we plug in numbers. KB, we're not given the KB, but we're told the Ka, and you need to remember the formula. Ka times Kb equals 1 times 10 to the minus 14. So Kb is going to be 1 times 10 to the minus 14 divided by Ka, which in this case is 1.82 times 10 to the minus 4. Just like a weak acid, the concentration of these two things is going to be the same, so we can just rewrite that as hydroxide ion squared, and the concentration of the methanoate ion is 0.075, which is what we worked out just before. So chuck all that in your calculator, you get hydroxide ion squared 4.12, square root that, and you get this. And once you've got the concentration of hydroxide ions, you can then work out the pH. You can go the long way, or you can be lazy like me and just work out what the pOH is. So the pOH is minus log 2.03 times 10 to the minus 6, and that gives you an answer of 5.69. And therefore, what is it going to show up? The pH is going to be 14 minus 5.69 equals 8.31. Alright, lucky last. Write a pH scale for the y-axis using the values calculated in A on the previous page. So you worked out that the pH of the weak acid at the very start was 2.28, therefore we're going to start about 2, and it's going to go up in ones. So 4, 6, 8, 10, 12. That wasn't actually worth a mark, it's just something for you to try and do. Part 2, circle the buffer region on the graph below. So what you'll see with this graph is it starts to rise steeply, and then it flattens out for a bit, and then it starts to rise steeply at the end. So the buffer zone is this kind of region here where the pH doesn't actually change particularly much, despite adding lots of potassium hydroxide. So putting a circle around that is what we're after. Explain how the species in the titration act as a buffer between these pHs. Now what lots of you did was you wrote equations to show how a buffer solution was actually able to absorb acid or base, and you wrote equations for it. But this is actually asking, why does a buffer form? How does it actually be a buffer? And the reason why is because it contains a mixture of your acid and your conjugate base. Okay, that is why it's a buffer, because it contains mixture containing lots of methanoic acid and lots of the methanoate ion. Outside of the buffer region, there's not enough of one of those species to behave as a buffer. Okay, so it might have lots of methanoic acid so it can absorb base, but there's not enough methanoic ion so that it can absorb acid. Alright, lucky last C, choose from the list below, best indicator for this titration. So indicators change at plus or minus 1 of the pKa. So you want the change at the equivalence point, which is 8.1 in this particular case. So you want the pKa to be between 7.1 to 9.1, and in this particular case, thymol blue ticks that box. So, hope that cleared up most of the answers. We'll put up, or we'll email out a copy of the assessment schedule as well. If you have any further questions, please go ask your chemistry teacher. Thanks for listening.